Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into the next major topic of our course, which we're going to be focusing on for a couple weeks actually, which is probability. Probability is really its completely own separate branch actually of mathematics, whereas statistics is its own branch of science. Probability is really its own branch of mathematics. The reason we're going to be investigating probability, though, is that it's a really, really important and useful tool for more advanced statistics, specifically for inferential statistics, and in what we're going to be doing in our class, what is called hypothesis testing, which is using statistics and using data to decide if there's evidence for claims in different types of situations. So probability is a really, really important tool for us. So we're going to spend a couple weeks trying to really understand how probability sort of works and some of the rules that abound in it, and basically how to use probability to our advantage. So in this video, we're going to just get some basic ideas about probability, as well as looking at some motivating examples. As I mentioned, probability is really its own big branch of mathematics, but what's interesting about probability is that it's something we encounter in everyday life very frequently, and we all generally have a pretty intuitive sense of at least how basic probabilistic situations should work. So let's look at a couple motivating examples, and then we'll get into some definitions. So let's start with this motivating example 1, something that's a very sort of basic example of a probabilistic experiment, a sort of probability-based idea. We're going to suppose you flip a fair coin once. So you have a coin and you flip it once. We want to ask ourselves, what is the chance or probability? Chance, probability, they mean the same thing. So what is the chance or probability that you get heads on that one flip of a coin? Well, what's interesting about this is that even without studying formally the mathematics of probability, we probably all have a sense of what the answer to this is, right? We would probably all say that this probability is equal to, well, probably most of us would say that the chance is 50-50, or there's a 50% chance. And it turns out that when writing out probabilities, you can write them out as percentages, like we would say probably conversationally, or you can write them out as decimals, or you can write them out as fractions. Now, the interesting thing is, even without studying probability, we sort of all can agree that the chance that you get heads on that coin is 50%, 50-50. But why is it 50-50? Where is that sort of coming from? Well, probably most of us would try to reason it out as saying that if we have this coin, there's two things that can happen, right? There's two different choices. You can either get heads or tails on the coin, and only one of them is marked heads, so the probability is sort of 1 out of 2. Then, of course, 1 divided by 2, or 1 out of 2 is a fraction. As a decimal, that is equivalent to 0.5. And we know that converting a decimal into a percentage gives us 50%. So when you're phrasing probabilities, and we'll see this throughout our investigation of probability, sometimes it'll be convenient to view a probability as a fraction, sometimes as a decimal, and sometimes as a percentage. All of these are equivalent. So in this case, we would say the chance or probability that you get heads on that single flip of a coin is 1/2, 0.5, or 50%. Now, in a few minutes, we'll come back to this example and sort of formalize exactly why this process, this 1 heads out of 2 possibilities, really is a proper and actually accurate way of measuring the probability. But for right now, I think we can all agree that this is what we would intuitively think for this probability. All right, let's take another look at a sort of different motivating example, another sort of basic probability situation, one that we're probably familiar with as well. So let's suppose, instead of talking about flipping a coin, suppose you roll a fair 6-sided die once. So you have a dice in front of you and you're going to roll it once. We want to know, what is the chance or probability that you get a number that is 5 or higher? Well, we can sort of think about this in the same way. We'd say that this probability, we know that on a dice there's 6 different sides, 1, 2, 3, 4, 5, and 6. We want to get a number that is 5 or higher for whatever reason. We know that the sort of sides that'll do that for us is the 5 and the 6. So there are sort of 2 sides out of the 6 that will do what we sort of want here. So this probability as a fraction can be viewed as 2 out of 6. Okay, if we type that into a calculator and do that division, we should get that that's approximately 0.333, which of course is equivalent to 33.3%. So we can report this probability as 2 out of 6, the fraction, the decimal point 3333, technically it's infinitely repeating threes, but we generally round to 3 decimal places here, or the percentage 33.3%. Okay, so these are two basic situations that we've probably all encountered before, flipping a coin, rolling a dice, and we're able to sort of just use our intuitive sense to get these probabilities. So now let's give ourselves some terminology, some definitions that explain exactly why the approach that we've been taking here is the correct one. All right, so here are some really important basic definitions about probability. The first term we want to introduce is what is called the sample space. The sample space of a probability experiment is a list of every possible outcome of that probability experiment. So if you ever are asked about the sample space, that's just saying list out every possible outcome, everything that can possibly happen in that probability experiment. The second definition that we want to be aware of is what is called an event. An event is simply a collection of outcomes that we want to study. It's basically the thing that we're hoping will happen or the thing that we're trying to measure the likelihood of happening. A little bit of notation, instead of writing probability when we're doing this mathematically, we use a little bit of notation. It's sort of similar to functional notation. We'll write a capital P of whatever the event is, and that'll represent the probability that that event occurs. All right, and the last sort of basic definition is a basic formula for probability. Now, this basic formula is going to carry us pretty far. It's not going to be the only probability formula we use, but we're going to be able to use it for quite a while. It does have one big limitation, though, and it's sort of in bold right here. If all the outcomes are equally likely in the sample space, so if every outcome in the sample space has the same chance of occurring, then the way we can calculate the probability of an event is very simple. We simply count up the number of outcomes in the event, in other words, the number of ways the event can occur, and we divide it by the total number of outcomes in the sample space. Okay, now these definitions definitely are a little bit more abstract. Like we said, we sort of were able to do those first two motivating examples intuitively, just with a sense of how we would think these things should work. Now this really makes that a lot more formal. So let's go back and take a quick look at those two motivating examples and try to make use of this terminology of sample space and event, as well as this notation of the probability, and also see why our calculations exactly match this basic formula for probability. So let's go back to those first two motivating examples. Okay, so on this first one where we flipped this fair coin, let's talk a little bit about the sample space first. So the sample space here, what were all the possible things that could happen? Well, we're flipping a coin, so the sample space, we could probably call it as heads and tails. There are really only two things that can possibly happen when we flip that coin. Are they equally likely? Well, we know that unless this is some sort of rigged coin, which we're assured it's not, that the chance that it comes up heads should be the same as the chance that it comes up tails. So these are equally likely. Check. So this is important right now because, again, that formula only works if the outcomes are equally likely. So by knowing that that's the case, we can apply that formula. So how would we write out this calculation a little bit more formally? Well, we'd say the probability, the event that we were interested in was that we get heads here. So we'd say probability of heads, and this thing in here, that is the event that we're studying in this problem. And we would say, okay, well, according to this formula here, we'd say how many ways are there for that event to occur and divide that by the number of outcomes in the sample space. And of course, we're able to use this formula because all the outcomes are equally likely. We just confirmed that. So how many ways can we get heads? Well, there's only one way. So this would be 1 divided by how many things are in the sample space. There's 1, 2. So we'd get that 1 out of 2. And notice that that exactly matches what we sort of intuitively figured out. Once again, you could write them as 0.5 or as 50%. So this would be the sort of more formal way of answering this question. Same result, but now just using the sort of terminology and ideas that we're going to be seeing as we move further on. Okay, let's try to do the same thing with the second motivating example, just to make sure we're comfortable with this terminology. So once again, we know we're going to get the same answer, but let's just see what sort of is going on behind the scenes. So let's talk about the sample space. So since we're rolling this fair six-sided dice, we can assume that the sample space are the numbers 1, 2, 3, 4, 5, and 6, right? One of those things is going to happen because the sides of the dice are labeled 1, 2, 3, 4, 5, and 6. All right, then we would want to make sure, are these equally likely? Absolutely, right? Each side of the dice has the same chance of showing up as any of the other ones. So the chance that we get a 1 or a 2 or a 3 or a 4 or a 5 or a 6 are all the same, so they are all equally likely. So we could say then the probability, our event was 5 or higher, so we could say 5 or higher. Once again, this in here is what we would call the event. And how do we do that? Well, how many ways are there for 5 or higher to happen? There would be the 5 and the 6. So that would be 2 divided by how many outcomes are there in the sample space overall? 1, 2, 3, 4, 5, 6. So it would be 2 out of 6, which of course, like we said, that's approximately 0.333, which is 33.3%. Okay, so again, not getting different results, just sort of showing how this more formal terminology can be used, making sure that we understand what that terminology means, and seeing that the sort of mathematics of probability agrees with our intuition about probability. Okay, now that we've done that, let's go ahead and take a look at some more interesting examples, still trying to do the same thing, but just that are a little bit more complex, have a little bit more going on in them. All right, so for this example, we'll sort of take our very first motivating example and just take it one step further. So let's suppose instead of flipping one coin, you flip 2 fair coins. So let's see if we can write out the sample space for this probability experiment and then use that to calculate the probability that you get at least 1 tails. All right, so for A, what does the sample space look like in this case? And we'll use this sort of notation. Sometimes you'll see a little like squiggly bracket that just indicates like a set of objects, and that can be useful for writing out the sample space. It's not necessary, but sometimes you'll see that notation. Okay, so what are the things that can happen? Well, we can sort of list them out. We know that maybe what can happen is the first coin comes up heads, and then the second coin could come up heads. So one of the outcomes would be that we get heads and then heads. What else? Well, we could get heads, and then the second coin could show up as tails. That's definitely possible. Certainly the first coin doesn't have to show up as heads, so it could show up as tails and then heads. Or it could show up as tails and then tails. All right, those 4 things right there are the 4 different things that can happen in this probability experiment. The first coin should show up as heads, and then the second one could come up as heads or tails. The first coin could show up as tails, and then the second one could show up as heads or tails. That's it. Those are the only 4 things that can happen there. So, are these all equally likely? Of course, right? They're all equally likely because we're saying it can either be heads or tails on the first one, and then either heads or tails on the second one. So all 4 of these are equally likely. All right, so then for B, to calculate the probability that we get at least 1 tail, so at least 1 tails. How would we do that? Well, we'd go up here and we'd find all of the outcomes that have at least 1 tails. So that would be, if we want to sort of mark that, that would be this guy here, and this guy here. These both have only 1 tails. This has 2, but all 3 of those satisfy getting at least 1 tails. So our numerator would be 3 possible outcomes out of the total amount in the sample space, which would be 4. And we could then write that as a decimal, 0.75, or as a percentage, 75%. Again, it doesn't matter. You don't have to write out all 3 of them. You can just leave it as a fraction, leave it as a decimal, or leave it as a percentage. In certain situations, as we'll see, sometimes it's convenient to leave it as a fraction. Sometimes it's convenient as a decimal. Sometimes it's convenient as a percentage. So right now, we're just writing out all 3 of them to make sure we're aware that they're all equivalent. But later on, we'll just be using whichever one is most convenient in the situation. Okay, so this wasn't too bad, right? The sample space was these 4 things. They were all equally likely, and we were able to calculate this probability. Now, something we should be careful with, and we'll see this as we go further, is that there are other ways to think about the sample space. Instead of writing it out like this, we could have said maybe the sample space, you just count how many tails you get. So if you think about it, there's 0 tails, there's 1 tail, and there's 2 tails. The danger of that way of thinking about the sample space is that those outcomes are not equally likely. 0 tails happens here, one tail happens here and two tails happens here. You can see that the one tails actually has two different ways of happening, so they're not equally likely. It's not an incorrect way of thinking about the sample space, but it won't allow us to use a formula like this. So we have to be very careful. We always want to try to write out the sample space in the most basic way possible, the most fundamental way possible, because that will make it most likely where all the outcomes are equally likely. All right, let's take a look at it taking this one step further, and then we'll move off of coins for a while, and let's talk about what happens if you flip 3 fair coins. All right, so we're going to try the same thing here. We're going to suppose you flip 3 fair coins. We're going to try to again write out the sample space, and then we're going to try to calculate the probability you get all tails. So for A, let's see if we can write out that sample space. All right, well, let's start to write out what they can look like. You could get heads on the first one, then heads on the second one, then heads on the third one. You could then go ahead and get heads on the first one, heads on the second one, and tails on the third one. I suppose you could then get heads, tails, and heads, or heads, tails, and tails. Now, if we think about that, that seems to have exhausted everything where you get heads first. So now there should be a grouping where you get tails first. So tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. That should be the entire list of things that can happen. What's sort of interesting, if you notice, is that these heads, heads, and then heads, tails, and then tails, heads, and then tails, tails, those were the outcomes of 2, and then we basically said the third one could be heads and tails, heads and tails, heads and tails, heads and tails. So notice that we have double the amount of outcomes that we had when we had 2 coins. So you can imagine, since we have 8 outcomes here, that if we did 4 coins, there'd be 16 outcomes. If we did 5 coins, there'd be 32 outcomes. It would keep doubling. Now that should warn you that as we go further, we're not always going to want or even be able to write out the entire sample space. Right now, we're able to do that because we have relatively simple probability experiments. Things don't have that many outcomes, but in the long run, we'll sort of avoid writing out the entire sample space. So right now, we're just trying to do the very basics, which includes writing out the sample space, but that's not something we're always going to be doing. All right. Are these all equally likely? For sure, right? It's just saying what happens on each coin, so they're going to be all equally likely. So we can go ahead and calculate our probability. We want the probability that we get all tails, so probability all tails. Again, this is our event of interest. So how many of these show up where they are all tails? It would just be this one here, only one of them. The one where it's tails, tails, and tails. So our fraction would be 1 out of how many outcomes overall? Well, we had 1, 2, 3, 4, 5, 6, 7, 8. So we'd have 1 out of 8. If we type that into our calculator, we could get it as a decimal, 0.125, and convert that, if we wanted to, into a percentage, 12.5%. So if you sit there and you flip 3 fair coins at a time, the chance that you're going to get all tails is 12.5%. So 12.5% of the time you would do this, you would get all 3 to be tails. Okay, so now, as again, the point of this is to show you guys that yes, even as the sort of event gets more complicated, we can just keep sort of expanding on what we're doing, though in the long run, we might want to sort of avoid that. All right, let's go ahead and change gears just a little bit. We've done some coins and some dice. Obviously, those are very sort of standard things that generate probabilities. We'll sort of always fall back to things like coins and dice and cards, very standard sort of probability generating things. But let's look at something that maybe is more related to some of the things we'll see in statistics, which often deals with choosing people or choosing people from a group. So let's take a look at an example like that. So let's suppose you have a room with 7 people in it, and we have some information about these people. So we have their names. They're Aaron, Bob, Cindy, Dave, Emma, Frank, and Gina. We also have their genders. So Aaron, Bob, Dave, and Frank are all males, whereas Cindy, Emma, and Gina are all females. And we also have their age. Aaron is 20, as is Cindy. Bob is 30, as is Emma. And Cindy and Dave is 40, Gina is 40, and Frank is 50. So we have their names, we have their genders, and we have their age. And we're going to imagine that you pick one person from this room at random. So we're going to try a couple things with this. And again, this is trying to take us that next step further about understanding sample spaces. So what we're going to do in part A is we're going to write out the sample space for this probability experiment in 3 different ways. So like I mentioned when we were talking about the coins, there are sometimes several different ways to write out sample spaces. Now, sometimes one way of writing it out is more useful than others, so we'll get a chance to sort of discuss that here. So let's think about these sample spaces. So one way, of course, is to go sort of the most fundamental. Each of these is a different person, so we could just say the sample space are all the different people. So we could say that the sample space is Aaron, Bob, Cindy, Dave, Emma, Frank, and Gina. Right? It's sort of most fundamental is our sample space. There are 7 people in the room, so the sample space is that you pick out one of those 7 people. But, of course, we might be more interested in focusing on one of their traits. So another way to sort of view the sample space is you could say, instead of caring about exactly which person it is, maybe you just care about the gender of the person you select. If you think about that then here, well, there's only 2 options for these people here. So our sample space then would be just male and female. So that would be another way of viewing the sample space. You either pick a person who's male or you pick a person who's female. Maybe you're not interested in their gender, maybe you're interested in their age. So a third way of viewing the sample space is that they could be age 20, age 30, age 40, or age 50. That's all the different ages for people in the room, right? We saw that there were some people who were age 20, there were some people who were age 30, there's some people who were age 40, and there's a person who age is 50. So all of these are different ways of viewing the sample space. So are some of these better or worse than others? Well, I mean, again, it depends on your view, but there is a big limitation to these two, at least from what we've done so far. The problem with viewing the sample space in these 2 ways is that these outcomes are not equally likely. There's not the same chance that you get a male as there is a female. Why is that? Well, we know that for males, there's Aaron, Bob, Dave, and Frank, 4 people, where for females, there's only 3, Cindy, Emma, and Gina. So these are not equally likely. Not equally likely. Same thing for the ages, right? There's 2 people who are age 20, 2 people who are age 30, 2 people who are age 40, so those all have the same chance of being chosen. But age 50, there's only 1 person. That means it's going to be less likely. So these are not equally likely. So we wouldn't be able to use the formula that we have so far to calculate using these sample spaces. In other words, we can't say that the probability that somebody is a female is 1 out of 2, because these are not equally likely. Same thing, we can't say that the chance that somebody is age 20 is 1 out of 4, because these are not equally likely. So if we want to calculate things, we're going to have to use this one where it is equally likely. Because here, each person is represented as a separate person, and we know the chance of choosing any one person is all the same. It's all equally likely. So let's make use of this sample space and actually calculate some probabilities here. So for B, we want to know the probability that we choose Aaron. So how would we do that? Well, that would be pretty easy, right? There's only 1 person. That is Aaron. That is 1 there. So, and then it would be out of the 7 people overall, because we're using this sample space where everyone is equally likely. 7 people. Again, you could just leave it as a fraction. If you wanted to, though, you could convert it as a decimal and get that it is approximately 0.143, which is 14.3%. Perfect. All right, let's calculate another one. We could say the probability that we get a female. Again, just because it mentions female doesn't mean we're going to use this one. We're still going to use this because it's equally likely, so we can use our approach. Let's go ahead and find the outcomes, or the individuals here that would achieve being female. That would be Cindy, Emma, and Gina. So there are 3 females out of the 7 people overall. If we then calculate that, 3 divided by 7, we should get about 0.429. which would give us 42.9%. So if we pick a person at random from this room, the chance that they would be female is 42.9%. And that's coming from the fact that we would achieve getting a female if we chose Cindy, Emma, or Gina, 3 out of the 7 people. All right, we have one more, someone age 40. So we want the probability age 40. Okay. Well, which people would achieve age 40? If we go back up here, we can remember that Gina was age 40 and Dave. So that would be Gina and Dave. So that would be 2 out of the 7 people. And if we calculated that, 2 divided by 7, I guess we could view that as 0.286, which is 28.6%. So there we go. We calculated the probability of each of these events. The chance that we randomly select the person Aaron is 14.3%. The chance that we get a person who is female, forgetting about which female it is, just as long as they're female, 42.9. And the chance that we get a person who is age 40, again, don't care who it is, as long as they're age 40, 28.6%. Okay, so again, the idea here, and we'll investigate this more and more as we go forward, is that a lot of times in a probability experiment, you can think about the outcomes in a lot of different ways, especially if you have more information. We knew who these people were by name, we knew their gender, and we also knew their age. But we have to be careful. If you plan on using this formula of just dividing the number of outcomes by the number of things in the sample space, you have to make sure that they are equally likely. All right, so let's go ahead then and talk a little bit about what we can do with sample spaces like this, where things are not equally likely. I mean, if we can't use them in this form, can we sort of add in the probabilities? I mean, we just calculated, for example, the probability of female is 3 out of 7. We should be able to do the same for male. It'd be 4 out of 7. And once we say that, maybe we could then use that. Well, that's the idea of a probability model. So let's give one more quick definition, and then we'll come back to this example and sort of talk a little bit about what we can do with these sample spaces. So a probability model is a list of all possible outcomes of a probability experiment. So you got to list out all the outcomes along with their associated probabilities. And we often use probability models when we list the outcomes and they're not equally likely, so that we can say, okay, they might not be equally likely, but at least we know what each of their probabilities are. When you build a probability model, they must follow 2 rules. I just should have a model in there. Probability model must follow 2 rules. One, and this holds for any time you guys are calculating probabilities, the probability of any outcome or event in that model is always between 0 and 1. And this is a good rule just to remember anytime you guys are calculating probabilities in this class. Whenever you calculate a probability, you will always get something that is between 0 and 1. That means no negatives for probabilities and nothing like 2 or 3 or 1.7. Probabilities always land between 0 and 1. Notationally, we can just say that anytime you calculate the probability of an event, it is somewhere between 0 and 1. If you ever land at those very edges, 0 and 1 exactly, well, they mean a couple things. A probability of exactly 0 means that you're talking about an impossible event, something that just simply cannot happen. That would be like flipping a coin and getting a 5. And when you flip a coin, you either get heads or tails. So it's impossible. The probability is 0 that you would get a 5. The probability of 1, if you ever get a probability of exactly 1, that means that the event you're talking about is a guaranteed event. That's like rolling a 6-sided dice and getting a number less than 7. That is a guaranteed event. It would be 6 out of 6, which is equal to 1. So you can sort of think about the spectrum for probabilities as going from impossible to guaranteed. The vast majority of probabilities we will calculate will be somewhere in between there, but they will never be outside of this range. All right, the second thing that has to be true for a probability model is that the sum of all the probabilities of all the distinct outcomes, so outcomes that are completely different from each other, that have no overlap, will be exactly 1. Notationally, again, we've seen this summation notation a couple times, not super important if you're not comfortable with it, but just to mention it again, the sum of all the outcomes of the probability of each outcome must be 1. Okay. So let's go back real quick and build a couple probability models for those other 2 ways of viewing the sample space. So if we go back over here, we'll sort of just pop this down here. So one way to do a probability model, if we sort of based it on this viewing of the sample space, is that we could say that the outcome for choosing a person from this room is that they either are male or female. And what are those probabilities? Well, like we said, the probability for male would be Aaron, Bob, Dave, Frank. So that would be 4 out of 7. And the probability for female, well, we calculated that was 3 out of 7. So this would be a way of sort of viewing this experiment, writing out a probability model for viewing the sort of important result was their gender, either male or female, probability 4 out of 7, 3 out of 7. What do you notice about those probabilities? Well, 4 out of 7 and 3 out of 7 are both fractions with denominators smaller, with numerators smaller than their denominators, which means that these numbers are between 0 and 1. So they satisfy the first rule of this. Do they satisfy this? Well, if you go back and you check, what do we have if we do 4 out of 7 plus 3 out of 7? It would total up to 1, of course. So this really is a probability model. Can we write up a different probability model? Sure, right? Instead of focusing on gender, we could go ahead and view the outcome that's important to us as their age. So age 20, age 30, age 40, or age 50. And we could write out the probabilities here. What's the probability that we get age 20? Well, age 20 would just be Aaron and Cindy, so it'd be 2 out of 7. Age 30, that would be achieved if we ended up selecting Bob or Emma, so that's 2 out of 7 as well. Age 40, that would be achieved if we ended up selecting Dave or Gina, so that's 2 out of 7 as well. And age 50, well, that would only happen if we ended up selecting Frank. That's 1 out of the 7 people. So another way of sort of viewing a probability model here would be focusing on the age of the person selected. There would be 4 outcomes. They're not all equally likely, 2 out of 7, 2 out of 7, 2 out of 7, but only 1 out of 7 for age 50. Does this satisfy the rules of a probability model? Well, for sure. Each of these is between 0 and 1. No negative numbers, no values greater than 1. And if you sum these up, 2 out of 7, 2 out of 7, 2 out of 7, that's 6 out of 7, plus 1 out of 7, that's 7 out of 7. Yep, that is equal to 1. So this is sort of 2 ways of building probability models if you want to focus on a trait that is not equally likely amongst the group. We're going to focus more on building probability models and making use of probability models in our next video.